Hello and welcome back. Today we're going to talk about the basics in MRI. So in order to begin with talking about the basics, we need to break things down a bit. So we're going to talk about hydrogen. Hydrogen is this active element in MRI. We love it because it's abundant, but the truth is we can use many different types of elements to produce some information from our patient in MRI. But we're going to stick with hydrogen. So why hydrogen? Yes, we know it's abundant, but in nature and in our body, it's in the form of what we call a protium, or an isotope of hydrogen. So it has one proton in its nucleus and one orbiting electron. Each hydrogen have what we call a magnetic moment, or this little magnetic field that's produced within it. And it has directional magnetism. Now the rate that this wobbling occurs is very important because we're going to use this rate in order to generate resonance in our patient. Okay, in order to predict this, we need to understand the gyromagnetic ratio. Now the gyromagnetic ratio is the rate of precession at 1 Tesla. Okay, so at 1 Tesla, hydrogen will precess at 42.6 megahertz. That's 1 Tesla. So that becomes very important. So now that we have some thought, some baseline of what controls this precessional frequency of hydrogen, we know magnetic fields do, and we know what the gyromagnetic ratio is, we need to kind of put it all together. In order to do that, we take our patient, and our patient is full of hydrogen. In a normal setting outside of MRI, outside of a magnetic field, those hydrogen are pointing in different directions. So these vectors are pointing in different directions. So they cancel each other out. We can't measure it. But if we place them in a strong magnetic field, a static magnetic field, we can start getting directional information from our patient in terms of hydrogen. Hydrogen will either align parallel or anti-parallel to this B0, or the vector of the static magnetic field. All right, so I like to look at this as kind of like a river, where the B0 is a current. So if the current in this river is going this way, if I place a boat in this river, this boat is going to float down this river based on the current that it's going. Right? So it's going to flow down this river. No resistance, it's very easy, it's going the path of least resistance. Now, there's always going to be some hydrogen that have a higher energy state, and they're going to defy this. They're going to have enough energy to paddle against this current. So they'll pedal against this current. We'll usually find more of these hydrogen, or we will find more of these hydrogen going with the current than against it. All right? So these are going to be the weak energy state hydrogen. They're not strong enough to defy this B0, but there's always going to be a few strong, higher energy state hydrogen that will be able to defy it. Again, it's more complicated than that. There's quantum physics involved in this, but we won't go there. We're just going to kind of be just basic. So we can see that if we're looking at this picture, there's going to be more of these hydrogen pointing with the B0 than against it. Okay, so what does that mean? That means that we can measure this. And so how is this possible? Well, magnetic fields cancel each other out. So it's kind of neat. But magnetic fields also are additive, so we can add them together. So if we have more of these hydrogen pointing in this direction than this direction, we have what we call a measurable magnetic field in this direction than against it. When we start to work with our patient, when we start to deliver RF pulses and activate gradients, we can start manipulating these vectors. But the important thing to remember is that we're going to have this net magnetism. We're going to have a majority of these hydrogen pointing in one direction, so we have a measurable amount of magnetism pointing in one direction, B0, than against it. All right. So for every magnetic field detected from this hydrogen pointing to the B0, and every hydrogen pointing against this B0, we're going to have basically a cancellation of this magnetic field, a non-detectable magnetic field from them. So we're going to be left with the difference, and that will be our net magnetism. Now at rest, we have this net magnetism given the field strength we're in. So let's change the situation for a second so we can better understand net magnetism. let's increase the strength of this current, right? Let's take it from, let's say, 1.5 Tesla to a 3 Tesla. Well, some of these hydrogen here that once had enough energy to defy this current, now they're faced with a stronger current and they don't have the energy to defy it. So they will flip and point along with our B0 or go with the current. And if that happens, we can have a higher net magnetism. We will have more of these protons pointing with the B0 than against it. So we have a higher net magnetism. Now, at rest, so in our patient, at rest, we call this equilibrium magnetization, where hydrogen are just sitting, given their field strength, and we have a set amount of net magnetism. And so in order for us to understand what we need to do to our hydrogen in order to increase an energy state of hydrogen to change this net magnetism so we can measure something. Okay, we have to measure something from our patient. We're measuring the magnetization in our patient. We're magnetizing our patient and we're measuring this change in hydrogen. We have to identify how fast these hydrogen are wobbling. And we use the MRI equation to do that. So in order to understand this, we need to basically say, all right, if I want to solve for what frequency we need to send to our patient in order to excite them, I need to go ahead and understand a few things. I need to know what the gyromagnetic ratio is, which we said is 42.6 megahertz. And then I have to know what our field strength is. And let's say it's 1.5 Tesla. Now if I multiply this 42.6 by our field strength, 1.5 Tesla, I'm given approximately 64 megahertz. So I know that at 64 megahertz, these hydrogen are, that's their rate of precession, 64 megahertz. All right, so we use the Larmor equation to help solve for that. Now at the council, you're not doing math, you're not solving for Larmor, for what the precessional frequency of hydrogen is, but it's something to understand if you're sitting for your exam. Now the RF pulse is going to be delivered to our patient from the RF transmitter. So we're going to deliver energy to our patient to increase the energy state of hydrogen. So we can change this net magnetism. So essentially in this analogy where they're on this river, it'd be like throwing them a Red Bull or an energy drink and taking these hydrogen, and now all of a sudden they have the energy to defy this river, and they're going to point in a different direction. And then we can see that this is going to change our net magnetism. And if we do this right, we'll drive down our net magnetism to almost zero. And we can watch what happens after that when we turn this RF pulse off. We stop generating RF. So the process of adding this energy to hydrogen is called resonance. All right? Resonance is all around us. But in MRI, we're basically just taking energy from one source and giving it to another source. But they have to behave the same way. The energy we send into our patient is only going to affect hydrogen that are behaving in that same manner. All right. So if we send a frequency of 64 megahertz into our patient, hydrogen precessing at 64 megahertz will be affected. They're the ones who get the Red Bull, the energy drink, to defy that current. So that's called resonance. When we do that whole process, we have a change of energy, right? So we just shifted our net magnetism, and we're going to shift that to the transverse plane. We're going to basically have our hydrogen, our vector is going to change from this B0 or longitudinal plane into a transverse plane. And we call that energy state transfer when this occurs. Now, hydrogen, when we deliver this RF pulse to them, they start behaving very similar. And when I say very similar, I mean that they're going to be pointing in the same direction, and they're also going to be wobbling in the same direction. And we call that phase coherency. So when hydrogen are in phase coherency, they're behaving the same way, they're in sync. All right, so after an RF pulse, these hydrogen are wobbling in sync, or in phase coherency, in the transverse plane. Now right after we turn that RF pulse off, these hydrogens start to decay. They start to move back into this longitudinal plane. They want to go back to that starting point. We call this decay of energy free induction decay. So as our signal starts to decay after an RF pulse, we start to see free induction decay, and we're going to talk a little bit more about that later on. So this whole process here describes just the basics of what happens to hydrogen during the entire process of being an MRI scanner, being excited, and then relaxing back to their starting point. Thank you so much for joining. I'll see you next time.
Please help and support our channel by clicking the subscribe and like button. If you want more content and special offers, Follow us on Facebook by clicking the link below. Thank you again for watching.